YouTube live telecast also happening. I'm going to post that in our Zoom chat. Please do share it with your friends who want to have it, as an extended program through the YouTube link directly.
Sir, I want to check my. Am I audible, sir?
Yes, sir.
Yes, sir. Yes, sir. Okay, sir.
Kartika madam is available. Kartika. Dr. Anand.
And just wait for a few more minutes. So we have to start the inaugural session, and then we will start the presentation.
Okay, perfect.
Sir, Mr. Ganesan, sir.
Yes, sir.
Give permission for Kirti, who is doing the prayer song.
Oh, okay.
His name is
I'm looking at that actually. Hold on. That's what I was looking at it much before. Oh, Kartika is there.
Yes, sir. Kartika.
Kartika?
Yes, sir. Yes, sir. Kartika.
Okay. I promoted Kartika as a panelist.
Then Kirti, sir.
No. Then
Prayer song.
is,
Okay, sir.
Kirti, right? Okay.
Yes, sir.
I did that now.
Sir. Kartika, madam.
Yes, sir.
Student has joined.
Yes, sir. Yes, sir. Kirti. Sir.
Kirti.
Yes.
Sir, Maunika.
Kirti, phone is unmute.
Sir, good evening, sir.
Good evening.
Sir, Maunika, she is going to sing prayer song, sir.
Maunika.
Maunika.
Sir Ganesan, sir, please unmute the Maunika.
No, I need to give her permission. Hold on. Monica, okay.
Yes, sir. சொல்லுங்க. எதுக்கு? ஆமா. வெளியே வந்துட்டு சொல்லிட்டு அப்புறம் க்ளோஸ் போயிருங்க. அது நல்லா இருக்கும். ஆமா, ஒன்றும் பிரச்சனை இல்லை, ஒன்றும் பிரச்சனை இல்லை. சார்ட்ட சொல்லிட்டு மாத்தி.
Can I start, sir?
Wait. Sir, one more minute. Monica, Kirti. Kartika madam, ready then? You please. Sir, battery run lower. Secret. Sir, 1 minute. Our director will join now. Pro chairman sir is join now. Kartika madam, you please check the Monica and Kirti mics so that we could hear. Monica?
Yes, sir.
Yeah, could you? Yes. Kirti? Your mic?
Yes, sir.
Yes. Yes, sir.
Kartika, okay.
Yes, sir.
No, I think, okay, anyway, I will, Kartika B, is that right?
Yes, sir, yes, sir. Please add.
Permission. Please, when you talk in, personal things, please unmute and talk. Hold on, Kartika B, hello.
Can I start, sir?
Oh,
Right.
yeah, go ahead, please.
Sir, our chairman sir is available. Sir, shall we start, sir?
Yeah, go ahead, please. We got 105 here and we got YouTube. A lot of people also joining. Thank you, sir. Go ahead, please.
Yes, sir. Principal, sir, shall we start the program?
Yes, sir. Yes, we can.
Yes, sir. Yes, sir. Pro chairman is ready, sir. Yes.
Yes.
Yeah, Kartika madam will start the program. Yeah, Kirti, start now.
Wondrous evening to one and all joined here. Now it's time for 3 days international summit on AI and machine learning in Industry 4.0 using IBM OpenPOWER and Power System along with PSNA College of Engineering and Technology. As the great Mother Teresa said, prayer enlarges the heart until it is capable of containing God's gift of himself. Do not make prayer a monologue, make it a conversation. Now it's time for prayer song. I welcome G. Monica, final year IT of PSNA College of Engineering and Technology to deliver the prayer song. Thank you, sir.
Mahaganapatim manasa smarami Mahaganapatim manasa smarami Vashishtavama Devadivandita Mahaganapatim महादेवशतं गुरुगहनुतं महादेवशतं गुरुगहनुतं मारकोटि प्रकाशं शान्तं महाकाव्यनाटकादिप्रियं मूषिकवागनमोदगप्रियं महागणपति.
Yes, thank you. Thank you.
Kindness is always fashionable and welcome. Leaders become great not because of their power, but because of their ability to empower others. I take this opportunity to welcome the man behind the successful department, Dr. A. Vincent Anthony Kumar Sir, Professor and Head, Department of Information Technology, PSNA College of Engineering and Technology, to welcome the dignitaries. Please, sir.
Yeah, thank you. The most respected pro-chairman, sir, respected principal, sir, leaders from OpenPOWER, the resource person, faculty members, research scholars, and dear student friends. A warm good evening to one and all. I welcome every one of you to this international summit on AI and machine learning in Industry 4.0 using IBM OpenPOWER in association with the PSNA College of Engineering Technology. I feel proud from the bottom of my heart in welcoming our chief guest, Rotarian Thiru RSK Raghuraman sir, Pro-Chairman PSNA College of Engineering Technology, who is the most dynamic and vibrant person, and most importantly, the driving force to all of us for achieving the milestone in almost every dimension of our profession. My heartfelt gratitude to our Pro-Chairman sir for having accepted our invitation and gracing this occasion with the presence as our chief guest. On behalf of the organizing committee, I extend a warm welcome to you, sir. I would like to extend a warm welcome to our most respected principal, Dr. D. Vasudevan, whose vision, interest, and hard work has once again proved in another success of organizing this kind of international summit in our PSNA CET campus. On behalf of the organizing committee, I welcome you, sir. A warm greetings to Mr. Ganeshan Narayanaswamy, the OpenPOWER leader in education research IBM system, who has supported to organize this international summit in collaboration with IBM OpenPOWER, and consistently we are working with IBM Ganeshan sir the last 1 year and before that to conduct this organize such kind of events. So on behalf of the PSNA College, a warm welcome to this program, sir. The Department of IT organizes consistently for the benefit of students, research scholars, for the faculty members to gain the latest domain knowledge in respective the artificial intelligence and as well as the machine learning. And we are working with the deep learning and other networks also. The objective of this international summit is to cover the areas of AI and ML for Industry 4.0 and to report the high quality and recent and original research work on industry application using AI and ML. The distinguished academic experts and a panel of experts from the industry has been called to share their perspectives in current state of the technologies to harness the power of the AI in long term with the participants. Our distinguished speaker is available with us, Mr. Andrew Osha, Cognitive Systems Architect, IBM Spain. And I'm very much delighted to welcome you, sir, in this international summit. And I welcome all the participants, the research scholars, students, faculty members, who have taken the much effort in attending this online international summit. Your active participation is very much important throughout the session. Through this summit, the participant will be able to have a clear understanding of the concepts of artificial intelligence, the machine learning, and its application in Industry 4.0. So once again, I extend my warm welcome to everyone. Thank you very much. Thank you. Kirti.
Sir, for your warm welcome. The best leaders not only inspire us, but develop and empower us to lead with passion. I am happy to invite Dr. D. Vasudevan sir, Principal, PSNA.
Sir,
Yes, sir. Yes, sir.
yes, sir. On behalf of the organizing committee, I invite you to give a presidential address for the summit, sir. Please, sir.
Yes, sir. Yeah. Good morning, good evening, good day to the participants throughout the globe for this great event on AI and machine learning with respect to specific applications towards Industry 4.0. Indeed, I am very happy to be here as a part of this inaugural function to this 3 days international summit on AI and ML. And in this platform, I want to share some of my views on this title and its wide applications and its necessity in the global business and the technical perspective. When I was invited and when the invite was handed over to us by the head of the Department of Information Technology of our institute, I had my own apprehensions about the title of the summit, because usually what is there is this machine learning is a subset of artificial intelligence. I just raised a doubt why always people are calling that as AI, ML and its applications. In some other cases, people are using a title of AI and deep learning. But a sort of clarification that it is a usual custom to have that. And to dig little more on the title, what is there for artificial intelligence in Industry 4.0? Industry 4.0 is akin with what we colloquially call as smart industries, where the industry itself is having its embedded intelligence, where we hope towards human-machine communication and machine-to-machine communication in the process of production itself. What the people are now looking towards is when the process happens in the industry, when a machine number 1, which is a predecessor machine of the machine number 2 in the continuous process, when a process deviates in the course of the machining, machine number 2 itself will communicate with the machine 1, or machine 1 is expected to communicate with the machine 2. There itself that deviation will be corrected. This is the ultimate expectation in a smart industry. Apart from that, the AI application is not at all limited to a single perspective. It is having an unlimited perspective in Industry 4.0. It is having a wide, it gives a new perspective to automation in the industry, because automation is the buzzword which increases the productivity. The productivity is the requirement of any industry in the world. So this application of artificial intelligence and subsequent applications of machine learning, deep learning in Industry 4.0 If I call that as industry 4.0, it is not at all limited to the big industries. Even the small and micro industries can have its applications. So if you apply this AI and ML in the industries, it gives a new dimension to the automation, and also it gives a new dimension to the digital monitoring and the control in the industries, control of the processes, control of the quality parameters, control of the process itself. And apart from that, it plays a major role in the predictive maintenance of the machine itself. So its applications is not a bounded one, it is unlimited one. It is a boundaryless. You can apply it the regular production, you can apply it the quality monitoring, you can apply it the machine correcting itself. You can apply it that a predecessor machine or a successor machining operation will automatically correct what is the fault happened in the previous machining operations. Like that, many things are expected in artificial intelligence application in industry. That is what expected in the industry front. This will give us a great deal in increasing the productivity, in decreasing the machine downtime, in increasing the process ability, capability. At the outset, it gives more production, more revenue, and more result in more wealth creation in the globe. That is what the people are expecting from it. And it is a buzz topic. It is a very attractive and the most required title in terms of industry requirement. And I am very greatly happy that our institute is having a 3-day true international summit on this title, where participation is throughout the globe. And I also thank Mr. Ganesan Narayanasamy, OpenPOWER leader in education and research in IBM systems, who had given a tireless participation and a good support to our institution to take our institution as well as our technical world, and also to have a exposure, to give an international exposure to our institute. For this, I want to really thank Mr. Ganesan Narayanasamy. Thank you, sir. And I also congratulate the team under the stewardship of Dr. Vincent and the faculty members and the students who had contributed much to organizing this type of event and this type of international summit. I also thank our pro-chairman, sir, who had given a support, good wholehearted support for this event. And in this event, we are going to get inputs from academia, like University of Wisconsin and NUS, and also we are going to get inputs from industries like IBM, Objection Automotive Limited. So for all these things will make this 3 days international summit truly international, as well as truly on ascendant intricacies in this title of AI and machine learning in Industry 4.0. I wish the summit a great success. I also ask the participants and our students and the faculty to derive most from this summit and take away this in their application into their projects. Thank you very much. Wish the 3 days international summit much useful and a successful one. Thank you very much.
Thank you, sir.
Endless words. Every thought you produce, anything you say, any action you do, it bears your signature. It's great honor for me to call Rotarian RSK Raghuram Sir, Pro-Chairman, PSNA College of Engineering and Technology.
An eventful evening to everyone on board with me. It is indeed a great pleasure in our end to organize an online international summit on artificial intelligence and machine learning in Industry 4 using IBM OpenPOWER power systems. First of all, my heartiest congratulations on this resourceful initiative, because artificial intelligence and machine learning are the most trending technologies which are used for creating intelligent systems today. Artificial intelligence is not just improving lives. In some cases, it saves lives. From importing smart infrastructure, healthcare system, smart agriculture, to feed a growing population, the reach of artificial intelligence is extensive in solving global challenges. So, the main objective of this international summit is to cover the areas of artificial intelligence and machine learning for Industry 4 and to report high quality, recent and original research work on industrial applications. We are happy to distinguish academic experts to speak on the current problems and technical aspects in the areas of research. In addition, a panel of experts from the industry has been called to share their experience, perspectives in current states of technologies to harness the power of artificial intelligence in the long term. I am sure you will have an enlightening experience with the speakers from global leading industry, Mr. Ander Ochoa, Cognitive System Architect, IBM Spain, and learned professor from reputed universities across the globe. We have received an excellent number of responses, around 850 online registration. We are glad to note that a steady stream of candidates, including doctorates, research scholars, faculty members, industry people, and students, are attending this international summit. This kind of exposure will definitely be a valuable opportunity for all the students to understand the industry scenario today. Wish you all a pleasurable learning experience and equip yourself to face the revolution in technology. I thank the organizers and the support from IBM. Thank you.
Thank you, sir.
Anything you say, any action you do, it bears your signature. It's great honor for me to introduce and welcome the chief guest of this evening. I take this opportunity and welcome Mr. Ganesh Narayana sir, OpenPOWER leader in education and research IBM system to deliver it.
Sir, please, sir.
Yeah, thank you, sir. Thank you for for the great opportunity to work with you on this, the summit. And this is a great initiative from PSNA. And I'd like to see these kind of initiatives going forward with many colleges and many universities worldwide. And I welcome everyone, whoever collaborated to have this kind of summit. And also I thank all of them, for spending good amount of time in everything, creating, presenting, and marketing, the event, worldwide. And with this, I'd like to invite my colleague, Ander Ochoa, who is the European leader for cognitive computing as well as virtualization, to start his presentation. And he has been with IBM for many years and has been an architect and delivered many presentations similar to this in Europe. And also lately, last 4 years, he has been working with me on many collaborative presentations and workshops across Europe. I welcome Ander to start his presentation. Ander, please go ahead.
Thank you, Eresan. Thank you, everybody from PSNA, for giving us the opportunity to share our knowledge with everybody. So, well, I'm going to share my screen. Let's see. Let me know if it works. Just 1 sec, please. Okay, looks like I have to leave the meeting and enter again to be able to share my screen. Just give me 1 sec.
Participants, hold on a second. Ander is joining again.
Hello?
Ander, yes, we can hear you.
Yeah. So, sorry for the delay, but my computer wanted me to restart Zoom to be able to share my screen for any reason. So let me use the PowerPoint and then I will show my desktop. Hopefully.
Yep.
Okay.
It's good. You are good
Perfect.
to go.
Thank you very much. I'm sorry for the delay. Well, first of all, I would like to introduce myself. As Ganesan said, my name is Ander Ochoa. I have been working, I'm right now cognitive systems architect for IBM SPIGI, meaning that mainly I work in the south of Europe, in Spain, Portugal, Greece, and Israel, but I also collaborate in other countries. I'm also an OpenPOWER Foundation member. And I'm here today to speak about SAP HANA, particularly SAP HANA on Power. So without further ado, let's go to the agenda that I'm going to try to follow today. First of all, I'm going to try to explain what's SAP HANA, because probably there is a lot of people who already know what is SAP HANA, but probably there is also a lot of people who don't know what's SAP HANA. So I will try to explain it and why we're talking about it today. Then I will try to speak about the relationship between IBM and SAP or SAP. And then after this, we will go for the more technical stuff. We will start talking about the IBM POWER architecture core differentiators for SAP HANA solutions. Also, I will talk a bit about the architecture differentiators and the infrastructure differentiators. This may look like the same, but you will see how it's quite different and how our IBM POWER or OpenPOWER architecture helps SAP HANA.
And one second, can you put it in a slideshow, because we are seeing, your entire view. Slideshow.
Okay.
Sorry for that.
Yeah, no problem.
Just swap displays.
Okay.
The swap displays, third in the top left. Yeah.
Yeah, is it working now?
We don't have your screen.
Those are the dangers of having too many screens at the same time. Let's see.
Perfect.
Okay.
Thank you, Samir.
Yeah, sorry. So at the end of the technical stuff, I will provide one small slide with some links to documentation that we provide for free, and for anyone who is interested in going deeper into IBM and SAP HANA. Also, I will try to answer as many questions as I can. But please, I will give you my email address in the first slide. So feel free to email me with any question or with anything that I can answer. So let's go to explain what is SAP HANA. SAP HANA, it's one software solution to manage everything inside one company. So SAP HANA can manage everything that one company buys, everything that one company sells. SAP HANA can manage everything that the company has in their warehouses. SAP HANA can manage the human resources, the financials, can manage anything inside one company. This makes it one very, very important tool inside one company. Also, it makes it as the primary source of all data. So for us, at least for us inside IBM systems, SAP HANA is a common word. However, it's something else. And I will try that everybody is in the same page here. SAP HANA means one software solution, as I said, that has 4 layers. The first one is just a common browser in our computer, and it won't be covered in this presentation. But then it has 3 more layers. The first one is a presentation layer called SAP Fiori. It's mainly for the user experience. Then it has another layer, which are the application servers, which could be 1 or more. And it's absolutely fundamental, part of the workload. And the last one is the database. And for me, this is the most important part of the SAP HANA workload. This database, it's a really, really special database, and it has several things that make it stand completely outside the rest of the databases. First of all, it's one in-memory database, meaning that it's always, the full set of data it has, it's always in memory, in main memory. Also, it's a compressed database. And this is also one fundamental factor for us to explain why our architecture works so well with SAP HANA. Then also it has other things that make it very special, like being columnar, insert only, and they are very interesting. However, it won't be covered in this presentation because it's quite it would require a quite detailed explanation. So this workload can behave in 2 different ways. The first behavior could be like one ERP. This is the OLTP, the online transactional process. And this is the typical behavior of the software when we buy something from one company, the company writes something in their system. This is the typical ERP, the day-to-day use. But also there is another type of behavior of this workload, and it's the business warehouse or the analytical, the OLAP. In order to explain this, I will let you know that at the end of the fiscal year, every company that has SAP HANA ERP, it downloads the whole data set and puts it in another database. This another database usually has a copy of the latest years of the company. It may be 3 years, 4 years, 5 years, whatever. It depends whatever the company needs. And in this new database, with such a big amount of data, they perform insights. They perform insights, they can predict things, they can get information of what has happened. Mainly, they use it for getting reports and letting know the management what's going on with the company. So it's a really, really important workload. The commercial names of those two behaviors, as I said, are for the ERP, it could be S/4HANA or SAP for HANA, and for the analytical one, it could be BW for HANA or Business Warehouse for HANA. Okay, so right now we are all in the same page. And why are we talking in one artificial intelligence and machine learning congress about this? Well, it's quite easy to explain. As I said, this management system, this solution, has the whole data that one company produces during the year. So it's a perfect repository, it's a perfect source for the data that we will use to create our models. And everybody who works with artificial intelligence knows that the models we create are as good as the data we use. And the best place to find the best data is in the subsystem. Typically, but we can get the data from the business warehouse, and we can run inference from the ERP. This is the typical way to use it. However, there are endless types of ways of using it. So now we know what's SAP HANA, and now I will try to explain the relationship between IBM and SAP. Are we partners? Are we lovers? What are we? Well, IBM and SAP HANA, we have been working together for a really long time. We have been working since SAP R3, for those of you who know it, and we have had a really successful story together. However, in the SAP HANA market, we have been quite late to it. But still, even if we have been a bit late, we have been a very successful company for this market. And I didn't have data for the rest of the world, but I had data for how we have behaved in Europe. And as you can see, the solution provided by IBM with our Power servers has managed to achieve almost 30% of the market, which is a really, really good figures, having into account that we were late to this market. And obviously, not only our servers, also our storage has been quite successful. And the storage is really important also because it has to be SAP HANA certified. Otherwise, it's not valid for running SAP HANA workloads. Anyway, here we are with 30%, and this makes us the only company that doesn't use x86 servers to run SAP HANA. So our offering is completely differential. Our approach is very different, but still it has been very successful. And as I said, IBM and SAP, we have had a long story, and they have recognized how well we do with a lot of awards. And I won't go with all the awards we have received because it wouldn't make to the end of the presentation. I will just stop in one. In 2018, SAP told us that we were offering their market the best infrastructure. And they gave us this award for having the best infrastructure for running SAP HANA. And this is not only the only thing they did. They did something, as the American says, they placed their mouth where, no, they placed their money where their mouth is. And what they did is SAP offers their customers one solution called the SAP HEC, which is SAP Cloud. And they decided to use Power servers for the biggest customers they have. So I cannot remember the exact figures. I think it's about 2 terabytes. Every customer that goes to SAP HANA, to SAP HEC, they put them in Power servers. And this is really good news because those customers are the ones who need more reliable computers, more powerful computers, and this is something very good for us. And it's only not only SAP who has decided to do this. There is a lot of examples of managed service providers all around the world. As I said, I have to apologize again because I only have data from Europe, or mainly from Europe. But this is a small list of managed service providers who have decided to offer their customers Power servers to run SAP HANA. And with this, I will end what I usually call the sales pitch of SAP HANA on Power, and I will try to go to more technical stuff. Okay, I'm going to jump this slide because I think it's too sales oriented, and I will jump to something more technical, which is where I feel more comfortable. So. Probably there is a lot of people in this conference who already have been introduced to Power servers, but probably there's also a lot of people who don't know what they are. So I will try to explain where are we, what we are, and how we perform. First of all, everybody knows x86 processors. Okay, they are used in a lot of servers, and the main builders for them are Intel and AMD. They are powerful, they are big, but also they are proprietary, meaning that no other one can build those processors. No other company can modify those processors. So it's a proprietary architecture, and it's a bit like you see here, something that one day it may disappear from the face of the earth. Who knows? But something has started happening lately that looks like it, and everybody knows Apple. Apple has decided to ditch x86 processors, and they have started using ARM processors, and very successfully, I would say. And those Apple products using ARM, well, ARM, it's a company that doesn't sell something physical. They just sell intellectual property, meaning that they just sell designs of processors, very good processors, by the way. And those ones who buy them, like Samsung, Apple, LG, Xiaomi, a lot of companies, they later on they can build them wherever they want. And ARM gets money in 2 ways: selling the design, and also when Samsung, for example, sells one of those processors, they have to pay between 1% and 2% of the price of the processor to ARM. So this makes it like a very expensive alternative. Even more, if somebody like Apple wants to modify the designs because they think that they can make them better, they have to pay even more. So there is a lot of money there that has to be paid to ARM. So the industry lately has been looking to other places to find something cheaper and to find something more reliable. In this case, this is the open architectures for processors, and we have 2 main examples of this. In one part, we have the RISC-V, which is a very, very interesting approach. It's a very young technology. I think it has something around 10 years, and it's mainly in the universities in the education environments. It has very few real-life examples of their processors, and those that exist, they are not very powerful. Still not, because it has a lot of momentum. So it's something to follow. But we have one very good alternative, which is the OpenPOWER. The OpenPOWER is the architecture of the power processors from IBM. Okay, well, during the presentation, I will use OpenPOWER or Power, and it's for me, it's the same. Okay, the Power architecture is something that started with the Power 9 in 1991, a lot of years ago, and it started as a proprietary architecture. Then years later, it became one licensable architecture, and now IBM has decided to open it to the whole world and to make it completely open, meaning that if you download the necessary data from the internet, you can build it wherever you want, in TSMC, in whatever company you want, and you don't have to pay royalties to IBM. And this is really, really interesting. How have we opened it? Well, we have placed the OpenPOWER architecture under the Linux Foundation umbrella, meaning that the same ones who work with Linux to make it open and to put it as one operative for the future, they also work with the OpenPOWER architecture. And also below the Linux Foundation, there is something that comes from when we were licensable, and it still hasn't disappeared, is the OpenPOWER Foundation. The OpenPOWER Foundation has a huge amount of participants. They are divided in different areas of interest for them. And they have very well-known examples as NVIDIA, Xilinx, Wistron, Tian, MSI, IBM, of course. Well, you can see here, they have a huge amount of people, very well-known people, and they all are pushing the OpenPOWER architecture towards new levels of performance. For the geek inside every one of us, I have decided to include this slide. This is mainly what IBM has given or has placed under the Linux Foundation umbrella. First of all, we have placed under the umbrella the OpenPOWER ISA, the instruction set architecture. This is the instruction set that the Power 9 that we will talk about today uses. Also, we have placed Microwatt, which is a software implementation of the Power 9 processor. This can be seen as one emulator of the Power 9 processor. It's not intended to run anything, it's just for development, okay? Yeah, and the version 3.0 is Power 9, and I think it's 3.1 was Power 10, which comes this year, at the end of this year. Also, we have placed the OpenCAPI. What's OpenCAPI? And this needs a lot of explanation. We will talk a bit more later on. The OpenCAPI is the Coherent Accelerator Processor Interface, which may look quite complicated, and I will try to explain it with simple words. When we add one adapter to one regular server, we are adding just one I/O interface that gets money moved from one side to another side. When we put one OpenCAPI compliant adapter to one Power 9 server, what we are doing is adding one coprocessor. And those coprocessors are accelerators. First of all, because they are based in FPGAs or ASICs. And second, because they have a huge bandwidth, they can have the same bandwidth as the regular Power 9 processors to the memory. So they can manage a huge amount of data. Also, last but not least, the OMI, the Open Memory Interface. And this is something that somehow liberates the CPU from the memory. Why I say this? Well, in x86 processors, the memory controller is built inside the same CPU. This makes the processor completely linked to the type of memory that their memory controller uses. With one OMI Open Memory Interface, we can put one, for example, one Power 10 processor, which is OMI compliant. We could add DDR3 memory, we could add DDR4 memory, we could add DDR5, GDDR, HBM, and check this out. HBM and GDDR is the memory that our GPUs have today. The same GPUs we use for creating models. This is the type of memory that we have there. So Power 10 could be something really, really important and very usable for artificial intelligence in very few months. So with this, everybody knows now what's SAP HANA, the relationship between IBM and SAP, and we all know how open our architecture is. So let's leave the OpenPOWER architecture at one side for the time being, and let's focus in SAP HANA. And in order to explain what SAP HANA and how it works, I will start explaining how a regular SQL query works in one traditional server. In one traditional database, and it could be anyone, DB2, Oracle, MySQL, anything, whatever. When we create one SQL query, we find that the whole data of the database is stored in the storage, in the disks, okay? So we have to move it to the main memory in order to answer the SQL query. So in the main memory, which is the fastest part of the server, we will have a small amount of cached data, a very small amount. If we have to go to the storage, it will take us a long and very precious time. So SAP HANA resolved this in a very innovative way. If you remember one of the first slides, I said that it's one in-memory database, and also it's a compressed database. As you can see, in the storage, the whole database is compressed. And then, as it's in memory, we move the whole data set to memory. So it will take, as you can see, it will make use of a lot of memory. But also, as it's compressed, we cannot use it right now. We have to uncompress it to be able to work with it. So we have to put it in the CPU, uncompress it, and then move it to one uncompressed work area. And then we can serve the SQL query. So this creates several bottlenecks that our architecture solves quite easily, at least for us, easily for us. First of all, if we have one in-memory database, we want to serve the SQL queries as fast as possible. So we need a very low latency and a very high bandwidth. Second, if we have to be compressing and uncompressing data the whole time, because we are going to serve a huge amount of queries, we need a very fast CPU and also very fast buses. And last but not least, the third point links the storage and the main memory. We are going to have to move from the storage to the main memory a huge amount of data. And well, there is as many sizes as customers, but we can find customers with terabytes and terabytes of compressed databases. And this makes the process of moving the compressed database from the storage to the main memory a very slow process. So slow that our company could be stopped during several hours moving the data from one side to the other side. And this is something that we don't want to happen. So we will see how we are going to solve those points. Please keep in mind those 3 points, and because we are going to talk now about all of them. First of all, the main memory. To be able to serve the SQL queries as fast as possible, we need a very performance memory system with the highest bandwidth possible. With the Power 9, which is the OpenPOWER implementation that we have today, we have up to 230 gigabytes per second of bandwidth. And this is per socket, okay? keep in mind that we have servers with only 2 sockets, and we have servers with up to 16 sockets. So this is a lot of bandwidth. Even 2 generations before, in Power 7 Plus, we already had 100 gigabytes per second. This is a huge amount of bandwidth. Our competitors' alternatives, they have up to 128 gigabytes per second. And this is not activating all the memory protection features that we already have activated. And that allows us to run the workloads without glitches, without bugs, without any problem at all. So you can see we have a huge amount of bandwidth. Also, the memory is fast, but in terms of CPU processing time, the memory can be quite slow. So in order to avoid suffering problems like what some processors of our competitors have, this problem is called the CPU starvation problem. This means that the CPU is doing nothing, waiting for data from the memory. We solve this problem using 4 different levels of cache memory: level 1, 2, 3, and 4. Each one of them, level 1 is the smallest but the fastest. Level 4 is the biggest, but it's slower than the level 3, but faster than the memory. This allows us to move the data very, very fast from the main memory to the CPU. And the CPU also is very fast. And obviously, everybody will say, oh, my CPU is the fastest one in the world. Well, it's not us who say that our CPUs are the fastest ones. It's SAP. If you compare our processors with the competitors' processors, you will see how SAP gives us one SAP score of almost 7,000 SAPs. While for the competitors, for the x86 competitors, they are below the 3,000 mark. This makes our processors really, really powerful. And I can guarantee you that those figures for Power 9 and also for Power 8, they are really, really conservative because they were taken not with our fastest processors. So we can perform really, really well running SAP. And why it is like this? Well, this is because we build our processors in a very new and innovative way. Instead of building them like a monolithic processor, as we already did in Power 8, or our competitors do in all of them, we create our processors as slices. Those slices can be seen as one full CPU. Well, this is not true because instead of 64 bits, we need 128 bits for the floating point operations. So we have to add 2 slices to create a super slice. With 2 super slices, we can create a Power 9 processor, and we can create processors with 4 slices or with 8 slices, making them really, really powerful. The good point of this is that each slice can run one thread. So those processors, the ones with 8 slices, can be configured to run one thread, 2 threads, 4 threads, or even 8 threads. This is because when we run one instruction through the processor pipeline, we are not making use of all the components of one CPU, of one processor. So we don't want to have anything stopped doing nothing. So we want to make use of all the possible resources in the CPU. So we can introduce 2 instructions at the same time, or 4 or 8. How it behaves? Well, as you can see here in the upper right side of the chart, you can see SMT1 could be the green column. This could be one of our processors running one thread, and it has a lot of power. However, if we run 2 threads in the same processor, we're going to see how even if the power of this thread is going to be slightly smaller, because at the end of the day, it's true that it's going to have to fight for some resources, but the addition of the two threads makes it a much more powerful processor. Exactly the same happens if we use 4 threads, and exactly the same with 8 threads. The processing power of our processor running 8 threads, as you can see, it's almost 4 times as running only 1. This is something that we have had since Power 8. We have it in Power 8, we have it in Power 9, and also we'll have it in Power 10. That will come later this year. So this approach allows us to create very different processors. And some of them can run DDR4 memory, which is really fast, really interesting. Sorry, very good memory. But it has one limitation. We can only build servers with up to 2 terabytes of memory per socket. This is something very good, but in terms of SAP, it's very small amount of memory. So we need more memory. So instead of using DDR4, we have decided to use, for some of our servers, not for all of them, but for some, we have decided to use buffered memory. This buffered memory allows us to, to offer more bandwidth, and also it allows us to use up to 8 terabytes per socket. This is a huge amount of memory. So as a small summary of the CPU, you can see that our processors are conservatively watching them. They are around twice the performance per core. We have almost 3 times memory per socket. We have almost twice the memory bandwidth per socket, and we have 4 times more of threads per core. This is the processor that compresses and uncompresses the data the whole time, among other stuff. And let's go to the third point, the one that linked the storage and the main memory. How we solve it? Well, since the beginning of 2018, the Power 9 processors have been built only using PCI Express version 4. This doubles the bandwidth of the PCI Express version 3 that most of our competitors still use. And also we use up to 48 lanes per server. This is a huge amount of bandwidth for I/O. And also, because we are using this type of very big PCI Express channel, we don't use, or we try, because we can, but we try not to use SATA, SAS, or SCSI drives. We are always trying to that our customers use NVMe. NVMe stands for Non-Volatile Memory Express Protocol. And the difference between NVMe and the rest of the protocols is that the rest of the protocols are serial protocols, while NVMe, it's a parallel protocol. It tries to take as much data from the source as possible and put it in the bus in parallel. This way, it can move a huge amount of data. We have them in as local drives, as NVMe over fabrics, different types of them. Now, also, I will try to explain the OpenCAPI that we started talking about at the beginning. But instead of explaining it, because it could be probably too tedious and too detailed, I'm going to give you one example of what we did in one of our labs. We took one of our Power 8 servers. This happened some time ago, so the figures that you will see here now, they have been, we have better figures with our newest servers, but at the time of this test was run, those are the figures that we got. We took one of the Power 8 servers and we linked it to one of our flash systems. The flash system is where we have all the storage. And in order to link them, we used one conventional HBA, the host bus adapter, okay? The same one that we can find in any server all around the world. So we moved the data from the flash system to the main memory of the Power server, and we were able to achieve more than 16,000 IOPS. I/O operations per second, with almost 500 nanoseconds of latency. Those are quite good figures, but they were not good enough. So we replaced this old HVA with one CAPI compliant adapter. This CAPI compliant adapter, let me remind you that it's something that has one accelerator, and also it has a lot of bandwidth. Just by replacing the HVA with the CAPI adapter, we were able to move from 16,000 to more than 100,000 IOPS. This is a huge increase just by replacing one adapter. And also the latency was reduced from almost 500 to 200. Everyone in the storage world knows that bandwidth is good, but the latency is what kills the storage. So you can see how this storage system performed really good just by changing the adapter. Okay, and let me repeat, please. Those figures are quite old, so right now we have better performing systems, but this is what we got at the time. And now that we have started talking about the storage, let me say very quickly that all our storage at IBM is SAP HANA certified. So whatever you select, you will be right. I always try to tell my customers to use Flash because it's the fastest one and it's the best performing solutions. The last but not least solution to try to break the bottleneck between the storage and the main memory is the persistent memory. Imagine that we have started our SAP HANA workload. So we have moved all the data from the storage to the main memory. And suddenly, for whatever the reason, we have to reboot the LPAR. The LPAR is the name we use for virtual machine. We have to reboot the virtual machine, and then we have lost everything we had in memory. We offer something called persistent memory, based in regular memory. The same memory that we use, we can configure it as persistent. What happens with the persistent memory? Well, the first day, we move the data from the storage to the main memory. We define it as persistent, and if we have to reboot the virtual machine, it will be still there. It will be persistent. It will not disappear. This is very interesting for companies that don't want to spend time moving the data from the storage to the main memory. And with this, I end the technical part of the differences, of the core differences, and I will start speaking about the architecture differentiators, because SAP HANA can be built in two different ways: scale up or scale out. Scale up is very simple to explain. If our virtual machine needs more CPU and memory, we just add more CPU and memory, and we continue running. And we can run as many virtual machines as we want in our scale up solution. For the scale out, if we run out of resources, we have to chop the database in two different parts. Let's imagine, for the example, that we are running a 4 terabytes database memory database, and obviously it fits in one scale-up solution, but in the scale-out, we have to chop it in 4 different parts, and we have to put 1 terabyte memory database in each one of the servers. This is one solution, but it may have a lot of issues, because the person who creates the pieces that we are going to put in the different computers or servers have to be really, really well designed. Otherwise, when we create a request, the data is going to start moving between servers. And you will see later on how this is a really, really bad thing to happen. Also, it's not only us who say that the scale-up solutions are the best ones. This is a screenshot of the SAP HANA website where they say, please, every time you can, use the scale-up solution, and only if you don't have other alternative, go for the scale-out. Why? Because, well, the whole point of having one in-memory database is to serve it as fast as possible. And this, in our biggest server, happens at 230 gigabytes per second and with 90 nanoseconds latency. However, in one scale-out solution, we have to put the network into the equation. And for the sake of this example, I have used 100 gigabit Ethernet network. And I still have to see one of my clients running 100 gigabit Ethernet network for their SAP HANA solutions, because most of them use 10 gigabit networks, some of them 25 gigabit, and a lot of them still use 1 gigabit Ethernet networks. But for this example, I used 100. With this network, if we have to move the data from one server to another, the bandwidth is reduced from 230 to 12.5 gigabytes per second. This is horrible. And if we, and then latency, you can see how it goes from 90 nanoseconds to 100,000 nanoseconds. This is something that we don't want. In our scale-up solutions, we can move virtual machines with up to 24 terabytes memory, which is huge, but the machines can handle up to 64 terabytes, so they can move almost 3 of those LPARs or virtual machines, so no problem for this. Also, our scale-up solutions offer something called co-location. This means that inside the same server, we can put 3 of the pieces that I talked about in the first slide. Do you remember SAP HANA was our computer, our browser in the computer, then a SAP Fiori, presentation services, then one application server, and then one database. Well, this database, our competition uses to put them, all of them, in each one in one separate server. This unlinks them using regular networks. This creates a lot of possible bottlenecks, a lot of points of danger. However, if you put everything inside the same server, you're going to use software-defined networks, which allow the virtual machines to communicate at memory speeds. No more network speeds, memory speed. This is how they can communicate really, really fast. In our labs, we have run this and we have seen that just by using, just by putting the application server in the same computer, you can increase the speed between 10 and 30%. So it's really, really good thing to have. Also, having a lot of virtual machines inside the same server allows us to share resources. We can share the CPU. So we, at the end of the day, we are going to need to use a lot of less CPU. This is very, very interesting for not paying too much. Also, our servers can handle a huge amount of virtual machines. Mainly, SAP HANA says that our servers are the only ones who can handle, with virtualization, up to 16 production databases. I have never seen a single customer with such a huge amount of production databases. Also, if we don't want to run 16 databases, we can run up to 15, but then we can add application servers, SAP Fiori. We can even add non-SAP HANA related workloads. Anything we want, we can run it in the same server. And why is it possible? Because of the hypervisor. Everybody knows VMware. Well, we don't use VMware. We use Power VM, which is way different. It uses a very few amount of resources. It's very secure, as we will see right now, and it can handle almost anything we throw at it. I wanted to add this as one example of one customer I worked for some years ago in the Nordics, in the northern part of Europe. The solution we created for him was based in 4 servers, and you can see the last one is the disaster recovery server running application servers and databases, and the other 3 ones, they run application servers, SAP Fioris, databases. They run a lot of stuff. And this is a very small amount compared to how much virtual machines we can handle inside one server. So the best thing of our servers is the flexibility. Power 9 servers offer the market a huge or an incredible level of flexibility. If one CPU dies, we can replace it automatically with other CPUs that are not that are waiting doing nothing. If one memory module dies, we can replace it live with another memory module that it's sitting there doing nothing. It's incredibly flexible. Also, our Power 9 servers, they run any kind of Linux. Oops. We can run Ubuntu, Debian, OpenSUSE, SUSE, CentOS, Red Hat. However, for SAP HANA, the only 35 solutions are SUSE and Red Hat. And we can run it with Power 7, Power 8, Power 9, and we will be able to run it also with Power 10. This is something very important because our competitors, for example, they have sold solutions for running SAP HANA 1, which was the predominant version some time ago. And when they tried to move to SAP HANA 2, they showed that their servers were not certified. So they had to throw them away and buy new ones. This doesn't happen with us. Also, we are really, really secure. And this is the last chart. This is almost the last chart that I will show you. This morning, I had this slide with 0 security breaches for Power VM because I had data from July 2013. But this morning, I said, hey, let's use real data from today. And this morning, I checked the United States database where every software vendor has to put all their hypervisors breaches. And this is the data I found. VMware has increased a lot. Well, all of them have increased the security breaches in one incredible amount. And just in December of 2020, it was discovered one hypothetical security breach for Power VM. So we have moved in almost 20 years from 0 security breaches to one hypothetical one. Well, still, as you can see, we are the most secure hypervisor in the world, no doubt about it. Also, our processors, they have suffered from meltdown and Spectre, but this is something that was fixed, and later on it has happened a huge amount of vulnerabilities that we have never suffered. But it's not something that our competition can say, okay? And I want to let you know what is inside the red circle. Patching bugs, when possible, because it's not always possible, always hits performance. So every time our competition patches one of those problems, they decrease the performance of their processors. This is bad news for them. So last slide, this is where we find all the documentation. I take a lot of documentation from those links. I will leave the presentation here with the links, and I encourage you to use the red books from IBM website because they are really good. They provide the most up-to-date information about SAP HANA on Power. And well, with this, I end my presentation, and I pass the control to Ganesan. And if you want to make any question, I will try to answer them. Mm-hmm.
Yeah, thank you, Hender, for the wonderful and very detailed presentation and sharing your experiences about SAP HANA on Power 9 enterprise servers. I'm sure these are the servers have been running in many industries as well as enterprises for several years. And certainly, there are a lot of opportunities also people to work on. Ander did share the Red Book related stuff also, IBM's Red Book on SAP HANA on Power. Please do take a look at it. And if you have any further questions, reach us out. And certainly, we are there to answer your questions too. And with this, I'd like to thank Ander again for his wonderful presentation. And thanks, Ander. And audience, interest of timing, because the next speaker, needs to get, minimum 30 minutes, to present this topic. So I'm closing, Anders stuff. Thanks, Ander, for the wonderful presentation. And there are some questions for you, Ander, in the chat window. Please go ahead and answer it. And now I'd like to invite Shamir Shante from University of Oregon, who is the performance director. And he has been a great collaborator with OpenPOWER and power enablement and ecosystem worldwide. He is also providing Power 9 system access, in various ranges, in his lab. If you need to have any system access for Power 9, you can reach us out also. Samir, please go ahead and start your presentation. Thank you for coming over here.
Thank you very much for inviting me to the PSNA College of Engineering and OpenPOWER Foundation. I hope you can see my screen properly.
Yes, Samir.
Yes, sir. Yes, sir. Yes, sir.
Okay, great. I will just start the slideshow. I have put the slides URL in the chat window. If you would like to download it, it's available from here. Today, I'll be talking about the extreme scale scientific software stack. And we are going to look at two main problems. The first problem is that with growing hardware complexities, it's now getting harder and harder to accurately measure and optimize the performance of our HPC and AI ML workloads. And the second problem is that with growing complexity, as our software gets more and more complex, it is getting harder to install the tools and libraries correctly in an integrated, interoperable software stack. So to address these two problems, the first product that I'll talk about is the Tau performance system from the University of Oregon. And it's a performance evaluation tool. It's a profiling and tracing toolkit that aims to support all the HPC platforms, compilers, and runtime systems. And it provides portable instrumentation, or the process of inserting hooks in your code, measurement, or using profiling and tracing, and the analysis or visualization of performance analysis tools like Paraprof and trace visualizers like Vampire from TU Dresden in Germany. We support a number of languages, including C++, C, Fortran, and Java and Python, and support automatic instrumentation. We support a number of different runtimes, GPU runtimes, including NVIDIA's CUDA, and we have analysis tools like Paraprof and Perf Explorer. Paraprof provides a 3D profile browser, which is unique to Tau, and we support the Power 9 platforms with NVIDIA GPUs. These include large-scale systems in the US, such as Summit and Sierra at Oak Ridge National Labs and Lawrence Livermore National Labs. So in case you're wondering, what can Tau provide, what kind of data it can provide, it can show you how much time was spent in each code region. It can show you at the routine level, at the outer loop level, and even within the loops, you can see where the time is being spent in each statement. The time spent in OpenMP loops, in threads, in kernels executing on GPUs. It can show you how much time it takes to run those kernels, how much data is transferred between the host and the GPU. It can show you low-level hardware performance counters, such as floating point instructions, level 1 and level 2 data cache misses, hits, branches taken, the extent of vectorization. It can show you the memory usage of your code. What is the memory footprint of your application? And by that, I mean the total memory footprint, including the stack, the heap, the data, text, BSS. You can see the high water mark of memory, energy usage, IO characteristics, even scalability of your code with Tau. And to add the hooks in your application, you can use source instrumentation using a preprocessor, using the program database toolkit, where you use different compiler scripts, such as taocc.sh, set some environment variables, specify selective instrumentation, filter files, and recompile your code You can use compiler-based instrumentation to add hooks at the routine level. You can also use preloading of a tau DSO, where instead of running your application, say an MPI application, such as MPI run application, you can say MPI run tau exec application, and it can intercept the MPI calls. It can add hooks to your code and use event-based sampling. This is the 3D profile browser of tau, the paraprof, where you can see the MPI ranks or threads along one axis. You can see the names of functions along the other. And then the height is the time spent in each function. So tau can show you the shape of the whole execution. You can identify unique things, one-off behaviors like this, and even zoom in between the two axes and see how much time was spent in this function on thread 199. The height is 129 seconds of exclusive time. So you can get detailed information at the level of MPI, pthread, OpenMP runtimes, even OpenACC and OpenCL. We have support for CUDA, Cocos profiling API, even Python. And you can mix and match the different runtimes in tau so that you could say, I want to use Cocos with pthread and MPI, or Cocos with OpenMP, and use the OpenMP tools interface to transparently insert the hooks at the thread level. Now, in case you're wondering what Cocos is, it provides abstractions for parallelism at the node level. So you may have heard that in high performance computing, MPI is the de facto standard for message passing between nodes. But what happens within a node? You have many different programming models such as pthread, OpenMP, CUDA, and Cocos provides a productive, portable, and performant shared memory programming model. It comes from Sandia National Laboratories in the US, and it provides a C++ API in which you can express your parallelism. It then uses aggressive compiler transformations to transform those Lambda functions in your program in using C++ templates into low-level backend targets such as OpenMP, pthread, CUDA. But this often creates a gap for performance tools. And so the Cocos profiling interface helps you bridge that gap and map the performance data. You can learn more about Cocos from this URL. And here is an example. Cocos allows you to use region descriptions to push and pop regions. You can use Cocos parallel for constructs to define the parallel operation and even give it a meaningful name. Now, this is a name that the developer encodes in the application in the source code and then compiles the code and runs the application. And when tau is used in conjunction with Cocos, it can then infer these names, it can extract the data, it can measure at the low level of abstraction, and then correlate it back to this source construct. And then you can see phases where all the function calls are flattened, and you can see the exclusive and inclusive time spent in each phase and all the timers that it calls within that phase. So that com update halo phase appears in tau's paraprof thread statistics table. Now we use a tool called tau exec to launch the application. And if you run your application like this with an uninstrumented code, then you could say tau exec-kupti, or you could say tau exec-ompt for OpenMP tools interface, and event-based sampling with resolution of file, function, or line level. The line level is the default. And you should compile it, your code with -g flag to get this. And then you will be able to see a profile where you can see phases which are meaningful to the user because they're encoded in the region descriptions. Then you can see what happens within that phase. And here is an example with samples taken in the strlen function on the Power platform. And you can see this view of Kibana MD a molecular dynamics code running on an IBM AC922 system, which has Power 9 CPUs with NVIDIA GPUs. And you can see the data transfers, you can see the MPI functions, and also you can see COCOS functions along with CUDA functions. So you can see the complete breakdown, and it allows you to delve deep into the code and then examine what each part of your application is doing, and even go down to the source level where you can see at this Kibana IMD source input.cpp at line 745, it took so much time. Now, tau has many environment variables that you can tweak to get different measurements, including tracing, call path profiling, if you want to track the memory footprint and other things. You can also use tau track signals to generate a signal in case your application has a problem and it generates a seg fault or something. So you can track exactly where the application is having problems. And you can specify different metrics for wall clock time and hardware performance counters. These are other environment variables with support for OpenMP tools interface. This is useful with the Clang compilers that are now available. They work well with the IBM platforms, and you can use the OpenMP tools interface with these compilers. And these are memory debugging variables that you can use. So in short, you can learn more about the tau performance system, tau being the acronym of tuning and analysis utilities. You can learn more about tau from our website, and it's all BSD style licensed, free to download. But with a powerful systems such as tau and other runtimes like COCOS, you may be wondering how difficult it is to install these tools and what we can do to address that problem about the growing complexity of tools, because it is now getting harder to install tools and libraries correctly in an interoperable software stack. And this is a problem that's something that we are dealing with at the largest scales. And here is the Department of Energy's roadmap to exascale systems in the United States. So we had pre-exascale systems, which includes the fastest supercomputers in the United States, which include Summit and Sierra. Summit is an IBM supercomputer based on the NVIDIA GPUs and Power 9 processors. It's situated at Oak Ridge National Labs, and Sierra is at Lawrence Livermore National Labs in California. And you can see that to date, we have only had NVIDIA GPUs in the largest class systems, and they are now exploring the use of other GPUs from other vendors besides NVIDIA as well. And the problem remains that as we want to install the software, what do we do? And to address this issue, we introduced the extreme scale scientific software stack. The software stack is comprised of software releases that are available for download in a usable stack from the e4s.io website. It's a curated collection. It's a curated collection of software. It has community policies. There's a documentation portal. There's a testing portfolio. We have build caches. We have quarterly releases and a turnkey stack. And we are looking at partnerships with other US agencies, industry, and international partners as well. So we use the SPAC package manager and create build caches, which can be used for bare metal installs. So you can download your applications, say on a IBM Power 9 system for the PPC64LE platform, and generate your installation using build caches. We also have container images that are available for download from E4S website, and also Docker Hub for Docker images. So we have base images and full-featured containers that support GPUs. And there are custom recipes so that you can start from a base image and then add more packages to it and create a custom image which is optimized for your needs. And we have support for GitLab and a validation test suite that we have developed. We also have a VirtualBox image to support multiple runtimes for those who are interested in looking at different HPC runtimes, such as Docker, Singularity, Shifter, and even Charlie Cloud. And we have images on GCP and AWS. Here is an AMI to deploy E4S. So there are three different areas of the exascale computing project. There is the application development, AD, software technology, and hardware and integration. And the E4S project comes from the software technology project. And it has many different technical areas. We have programming models and runtime, SDK, which I lead at the University of Oregon. And we have development tools, math libraries, data and visualization, software ecosystem, and the NNSA software technology projects. We have many different products, and we work on these products that the applications need now and will need in the future. And this includes some very well-known and widely used high-performance computing products, including MPitch, OpenMPI, PETC, Trilinos, and even some lesser-known, lesser used but known products such as Cocos, Raja, then SPAC, and then there are some new products that are emerging, such as SICM, ZFP, Unify, CR. We have examples like MPI, OpenMP, performance portability, libraries, LLVM, and this is very interesting that they have recently integrated the Fortran Flang compiler in the LLVM toolchain, and the Department of Energy has a special DOE LLVM fork. We have performance evaluation tools such as PAPI, Tau. We have math libraries such as BLAS, HDF5 for I/O, data and visualization tools, including ParaView. And all of these are integrated in layers using the software development kits or SDKs to create the extreme scale scientific software stack. So we have these community policies. If you would like to contribute a product to the extreme scale scientific software stack, and you can look at these policies over here. And there are 9 of these policies which span things such as validation. It includes SPAC-based products, product metadata, test suites, error handling, and so on. You can learn more about it in the policies page. And we have some phased releases. We have just released 21.02 release of E4S, which has 67 full release products along with the LLVM DOE based on version 13 of Clang. So E4S is a community effort to provide open source software packages for developing, deploying, and running scientific applications and AI applications on HPC platforms. We also aim to enable uniform APIs where possible, and we use the SPAC package manager. Our goal is to accelerate the development, deployment, and use of HPC software. We use the SPAC package manager for software delivery. It provides the ability to specify different versions of the packages, and it's a build layer, not just for E4S software, but also for a large collection of tools outside of E4S. And the reason for this is that scientific software is getting extremely complex. This is the dependency graph of NALU. It's a CFD code, a generalized, unstructured, massively parallel, low mark flow solver. And you can see that here is deal2, a C++ finite element library. And the complexity is growing, and all of these packages need to be installed in a consistent manner. This is the graph of RMiner, a data mining library. And even proprietary codes are using many open source libraries, and these are shown in blue. So we are building an entire ecosystem of software, including, say, over 15 applications, which use over 80 software packages on many target architectures with different compilers and programming models and different versions of each package. And so we have a combinatorial explosion of over 1.2 million installations if you have to build everything with all the versions. And each package has its own stack of dependencies. And right now it is getting to a point where many HPC centers are dedicating several FTEs to just build and support these applications. And they often trade the reuse and usability for performance. So we must make it easier to rely on other people's software. But in case you are wondering, how is it that we install software on a supercomputer? Well, you first download all the packages in tarballs and start building. And it looks like this. You start with all these 16 packages, you configure it, make it, you fight with the compilers, you tweak configuration arguments, then again you install all of these packages to then finally run the code, which may segfault, and then you have to start all over again. And if you're wondering, what about modules? Well, modules allow you to access a package that somebody else has already installed, and they just set up your path, LD library path, but somebody has to install the package. So SPAC is the flexible package manager for high performance computing. And you can just install packages such as Tau using SPAC by just cloning this URL and sourcing the environment files, and then you are able to install Tau. But it's also possible to specify different versions and compilers. So when I installed a package using SPAC, I first check the compilers that are available on the system using a SPAC compiler find, look at external packages such as CMake, M4, and other system utilities, and then I can install the package such as Tau. Now this is a spec, but I can specialize it. So I can say, please install Tau version 2.30.1 using this @ symbol. And then I can specify the compiler dependency using the percentage. So SPAC understands compilers, it understands versions. Again, I can say GCC @730. So that would be the version of GCC with Tau version 230.1. And then I can enable other flags such as MPI, Python, pthreads. These are variants in a spec or a recipe of Tau. And then I can even specify what provides MPI. So I can say a caret symbol for MVAP-H2 version 2.3 without the wrapper R path, and I can provide dependency information. So unlike other package managers, SPAC provides easy way to install a package, specify its versions, and also specify compilers and dependencies. With this, we can build a whole stack of packages. Here is Trilinos version 13.0, and I can say SPAC find, and these versions and multiple versions of the same package can coexist. That is very nice of SPAC in the way it layers the packages, and binaries work regardless of the user's environment. SPAC also creates module files. So if you feel more comfortable using modules, you can use those. You can learn more about SPAC from this web page. And we use SPAC to develop the software development kits, SDKs, in a number of these different areas. And all these technology areas contribute packages such as Tau from the tools and technology portion of the ECP portfolio of tools into the extreme scale scientific software stack. And multiple SDKs use the same cycle of develop the package, build it, test it, and then deploy it. And then we integrate it and then generate the E4S set of packages that you can download from this e4s.io. Now, it provides different components, including a curated release based on SPAC, but there are also bare metal installs and custom container builds. We have GitHub recipes for custom images, a validation test suite, even a doc portal. And in case you're wondering what are containers, well, a container is a lightweight collection of executable software that encapsulates everything needed to run a single specific task. What is interesting is that it does not have the OS kernel, and it's based on Linux. So the difference between a hypervisors and the containers, where you can use virtual machines with their own operating systems, versus containers where you don't have the operating system part within the container. So you use it on the host with its host operating system and deploy the containers. These are containers that are available, and you can just do a Docker pull. And here's a container image with different packages for different runtimes. And you also have Singularity support in E4S. And we have containers for PPC64LE, IBM Power 9 platform. And you can see these GPU Docker containers on dockerhub.com. And here are 67 E4S products for the Power 9 platform. These include packages such as Amrex. They include packages such as Caliper, GasNet, HPC Toolkit, Cocos kernels. We have MFEM, PDT, Tau, Sundials, Strumpack, Trilinos. 67 of these packages all pre-installed in a container that you can download from the website. And it has support for NVIDIA GPUs. So you could say Singularity run --NV and then point to a Singularity image file, and then you will have the full environment and you can access these packages. So if you start from a system that doesn't have all the packages installed, all you have to do is install one single file and Singularity, and then you have the full software stack available on the Power platform. Here is an example where I'm running the Singularity based image, and I can say Python, import TensorFlow, PyTorch, OpenCV, Matplotlib, even check if the GPU is available, and it can see the V100 GPUs. So it has the full software stack of HPC packages as well as AI tools like TensorFlow that use the NVIDIA GPU, and PyTorch are pre-installed for you. And you can get base container images and build your own from there. Here are some recipes for multiple platforms where you can say, start with this image and then this work directory, and then copy a spec.yaml file that has a full recipe of the packages you want to install, a listing of all the packages, and then you can just say, run this. So this is a Docker file that is used to create a Docker image. And there are multiple files with different platforms for different platforms like this. And here is a spec.yaml file. Here I can say that I want to use all of these packages with these versions. And then I can just say spec-e environment install, spec-e dot install, or I can use the same spec.yaml file and then say a Docker build with the Docker file like I had shown before. So you can create containers or bare metal installs from a spec recipe. And this is the E4S recipe of the packages. We also have binaries. So you can skip the building from source stage for different operating systems. And you can see for Power 9, there's PPC64LE. In total, we have over 37,000 binaries. And you can see which architectures, operating systems, compilers, and the full hash of these images. This is for the Amrex package 21.03 or March 2021, the latest version of Amrex. We can speed up bare metal installs using a build cache. Here are examples of how it's being used in the WDM app. And here is an example of the use of E4S in Pantheon Science application at Los Alamos National Labs. It's not enough to just install these packages. You want to make sure that they are installed correctly. And so we have a validation test suite where we have examples. This is a set of examples for the Magma package. And we have scripts to clean, compile, and run the application. And then it uses different parameters. We also have a LLVM validation test suite for the DOE fork of LLVM. And this is how you can create a full base, starting from a base image, how you can create a full container build for different compilers, MPI, and the specs here. And we also have GitLab integration with many of these runner images in E4S. You can find this using ECP E4S on Docker Hub. And this spans multiple platforms. Here is a GitLab instance running the workflow for, say, Red Hat, Enterprise Linux, and others on, say, PP64LE. And you can see the full set of builds that are happening for E4S. This is a multi-stage E4S build pipeline on Cori at Berkeley Lab at the NERSC Supercomputing Center. And this is at Oak Ridge National Laboratory in Tennessee in the US. You can see different builds. We also have a single location for accurate product descriptions for the ECP software products in the E4S doc portal. And you can search for different libraries, and you can then see the details about the name, summary, functional area, description. And we rake these GitHub websites of these packages every night. So the product information is all very fresh, and you can see the latest information of all the packages directly from the GitHub sites. And there are ways to specify your product in a .e4s directory where you can specify what files are being accessed. And you can learn more about it on our doc portal over here on the E4S webpage. We have a virtual box image where container runtimes such as Docker, Shifter, Singularity, and Charlie Cloud come pre-installed. And we even have a tool to simplify the launch of MPI jobs in E4S containers. And E4S containers support replacement of MPI libraries using this MPitch ABI compatibility layer. And this is the architecture. So I would like to stress that in summary, E4S is not a closed system for taking contributions only from DOE teams. It is extensible open architecture, which accepts contributions from US and international teams. We are looking for collaborations. It's a full collection of compatible software capabilities and a vehicle for delivering high quality reusable software products in collaboration with others. We look at it as a conduit for future leading edge HPC software targeting scalable next generation platforms. Our future work includes improvements in the support for GPUs, visualization tools, LLVM, facility deployments, scalable startups, launching of MPI applications, binary build caches, and Singularity and Docker images that we are now making available. This work goes on at the Performance Research Laboratory at the University of Oregon. I direct this Performance Research Lab, and this is located in Eugene on the west coast of the US. I would like to thank our sponsors, including the Department of Energy, the Department of Defense, National Science Foundation, NASA, and CEA in France, and the Exascale Computing Project that sponsors this E4S project. And with this, I'll take any questions you may have.
Samir, thank you very much for the wonderful presentation on E4S and on IBM Power 9 and OpenPOWER system. And definitely there are people, asking some question also in the question window, question and answer window. And certainly, the presentation is very important for a lot of beginners as well as who are interested in collaborating with the University of Oregon on TAO and E4S.
It is an example of yes, go ahead.
Yeah, with this, I'd like to again thank you for your wonderful presentation and really appreciate it. I know that it's early in the morning for you, and even then you are coming forward and presenting in this venue is very important. Really appreciable.
Here is an example of E4S running on our IBM AC922 system. You can see that when you run this image, you can access the GPUs, you can see which packages are installed. These are all these packages, including TAO, and you can see the modules. You can load LLVM, the DOE fork of LLVM, which is the latest 13.0. You can run Python, you can import packages like CV2, TensorFlow, check the access to the GPUs. This is the Tesla V100. And so you can see various packages installed over here. And it is possible to analyze other hardware besides servers using TAO. To answer your question, Prabhu, you can use it for laptops, you can use it for desktops, you can use it on any of these platforms. And thank you very much. Thanks for inviting me. And if there are any other questions, please feel free to email it to me. I have shared my PowerPoint slides.
Yeah, thank you, Samir, once again. And Professor Vincent, actually, do you want to start the vote of thanks and other procedure?
Yes, sir. Thank you very much, Professor Sami. And it's a very, very wonderful session. And really, I think you have given a lot of explanation about the IFO features and the tech access and how to the packages for the, and as well as the installing the software on the supercomputer and the Docker image visualization tools. And they are definitely the research scholars who is working about in the visualization or in the OpenPOWER. Definitely they'll use the lecture. And thank you very much, sir. On behalf of this committee, organizing committee, I once again thank you very much for. I think as a professor, the Ganesan sir has stated that in the early morning, I think you took a lot of pain and giving us a lecture. It's really we are amidst the honor and very much thank you for thanks for the session, sir.
Thank you very much, Dr. Vincent, and thank you, PSNA College of Engineering Technology and IBM.
Yeah.
Appreciate it.
Thank you, sir. Thank you, participants. I think we can share the quiz questions in the chat window. The participants, you can go through the quiz, and within 15 minutes time, we'll close it out. So those who give the correct answer, as announced in the earlier, you'll be receiving your t-shirts with the logo of the PSNA and the International Summit with the OpenPOWER, and as well as the e-certificate by tomorrow during the second day session. So I request all the participants, you please go through the quiz, which comes from the questions from the resource persons who delivered the lecture, and give the answer within 15 minutes time. Whoever gives the first and the most all the questions, and we can give the t-shirts. And the tomorrow session, the day 2, I think here we have a wonderful session from the Mrs. Clarice, Cognitive Architect, IBM USA. Tomorrow we start the section exactly by 6 o'clock. So I request all the research scholars and the students and as the faculty members, we join the session tomorrow by evening, exactly by 6. And the second talk by Orgaya, a professor, University of Wisconsin, exactly we start by 7 o'clock. So I thank all the participants. Now I think in chat window, I'll share the question. So thank you very much, Ganesan sir. I think
thank you, sir.
Yeah,
thank you, sir. I think the program went very well today.
Yes, sir.
Sure.
Yes, sir.
technology feast from various places, from Europe, US, and in India.
Yes.
And some people from Dubai and Singapore also joined as part of this
Okay.
program.
So I am sharing the questions, sir. Yeah.
Yeah, people are asking for the feedback session, link also.
sir.
Please do provide. Yeah. So we
this
have.
is the quiz and as well as the feedback form.
Oh, you have to share it to all the audience, sir. There is a
Yes, sir.
pull down.
Where?
There is a pull down
Yes, sir,
in the
yes, sir,
chat.
yes, sir.
Panelists and attendees, right? In that panelists and attendees, you have to say.